Today we're going to continue our lesson on the organizing principles of the periodic table. So we have several objectives for today. Our first objective is to understand how the number of protons an element has determines the order of elements on the periodic table. Our second is to understand how filling electrons into electron shells helps us understand when we move to a new row on the periodic table. And our third objective is to understand how the number of valence electrons and the number of electron shells that an element has can be determined just by looking at its position on the periodic table. So before we get started, let's do a little bit of review. I'd actually like you to pull out your notes and copy this table down into them. We have three subatomic particles that we really care about for chemistry: protons, neutrons, and electrons. Now, protons are positively charged. You can think of a proton as having a charge of +1. Electrons are negatively charged. You can think of an electron as having a charge of -1. And neutrons are neutral. They have no charge. You can think of a neutron as having a charge of 0. Protons and neutrons are both located in the nucleus, while electrons are located in the electron cloud. It's important to note that the electron cloud is vast compared to the nucleus. If you imagine the nucleus of an atom as a marble on the 50-yard line of a football field, the electron cloud is the size of the rest of the field. So the electron cloud is huge compared to the nucleus. Both protons and neutrons have a mass of 1 atomic mass unit, while the mass of an electron is so small that you can basically ignore it. It's negligible. Last lesson we learned that you could figure out the number of protons an element has by looking at the atomic number of that element on the periodic table, that you could figure out the number of neutrons that an atom has by taking the atomic mass, rounding it to the nearest whole number, and subtracting the number of protons from that. And we learned that you could find the number of electrons because it's going to be the same as the number of protons, at least for a neutral atom. That's because if the atom is neutral, if its charge is 0, well, then the number of positives and the number of negatives must be the same. Otherwise, I would have a charge that wasn't 0. Now, today we're going to start by talking about the most basic underlying organizational principle, which is to say the periodic table is arranged from left to right according to the number of protons that each atom has. So for example, hydrogen, that's element number 1. It has 1 proton. Helium is element 2. It has 2 protons. Lithium is element 3. It has 3 protons. By definition, any atom with 3 protons is lithium. Having 3 protons is what makes you a lithium atom. If you have 4 protons, you're not lithium anymore, you're beryllium. So the number of protons is what determines which element you have, and the periodic table is arranged from left to right according to the number of protons. Now, it's important to note, this would basically give us a list, right? So I could make a list in order of the elements. But in order to turn that from a list of going, hydrogen has 1, helium has 2, lithium 3, beryllium 4, boron 5, carbon 6, nitrogen 7, and so on, to change that from a list into a table, I need to know when to start a new row on the periodic table. And that's going to be our topic for today. When do we start new rows on the periodic table? So, to understand that, we need to talk a little bit about electrons. Now, we're going to be using the planetary model a lot in this class because this model is very useful. It's important to note that this is a model. Atoms don't actually look like this. This is just a useful way of thinking about how atoms are. This is like a map of an atom. In the same way that if I give you a map of California, that isn't the same thing as the physical earth on which you walk, this model of an atom isn't actually what atoms are like. It's just a useful abstraction that helps us understand atoms. So in this particular model, this planetary model, we tend to arrange electrons into these beautiful shells. So here you can see I have 2 electron shells around lithium. Each of those shells can hold a certain number of electrons, and you always fill the inside shells first before you move out from there. Now, if you have electrons that are in the outermost shell, those electrons are special. We call those valence electrons, and we especially care about them because the electrons on the outside of an atom are the electrons that can get involved in chemical reactions. So the number of valence electrons that an atom has is really important for predicting what its chemical properties might be. So here we have a lithium atom. Lithium has one electron, just one right here, in its outermost shell. So we would say that lithium has one valence electron. You can also see that there are two shells, 1, 2, so lithium has 2 electron shells. So I said each of those shells can hold a certain number of electrons. That first shell, the innermost one, is very small. It can only hold 2 electrons. The second shell is a little bit bigger. It can hold up to 8 electrons. Now, if you fill both that first shell and the second shell, then we would start putting electrons in the third shell, which can also hold 8 electrons. But remember, you always have to start by filling the innermost shells first. Only once those innermost shells are full can you move out from there. So now we have a reason why we can end rows on the periodic table. So before we just had a list of elements in order: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, etc. Now we have a reason why we can move to a new row on the periodic table. So remember that innermost shell, it can hold 2 electrons. So hydrogen has its valence electron, its one and only electron, in that first shell. Helium has 2 electrons. They both go in that first shell. At that point, the innermost shell is full. So if we want to have one more electron, like say lithium, which has 3 protons and 3 electrons, it now has to put that one extra electron in the next shell out. So when we move from helium to lithium, we're adding another shell of electrons. So each time you reach the end of a row on the periodic table, what we're doing is we're adding another electron to a new shell around the atom. And remember, rows are horizontal, columns are vertical. So every time we reach a new row, that's when we're adding a new electron shell to our periodic table. So what this means is that each row on the periodic table represents a number of electron shells. Lithium and beryllium are both in the second row. So looking at my periodic table, lithium and beryllium are in row 2. Sodium and magnesium, however, are in row 3. That means lithium and beryllium, they have 2 electron shells. Sodium and magnesium, they have 3 electron shells. So here we can see those atoms drawn out. And again, you can see lithium and beryllium in row 2 of the periodic table have 1, 2 shells, while sodium and magnesium in row 3 of the periodic table have 1, 2, 3 shells of electrons. Now take a moment and look at what are called the A groups on your periodic table. So if you look at your periodic table, you will see at the tops of the columns, they say things like 1A, 2A, 3B, 4B. If you skip over that middle section, you'll have what we call the A groups of the periodic table. These are the groups that are particularly well explained by this planetary model. The truth is that middle section is more complicated, and you have to learn a much more complex model of the atom to really understand those. But for the A groups, which is to say the column that hydrogen and beryllium are in, those 2 columns on the left, and the 6 columns on the right, this planetary model is a really good explanation of what's going on. So, if every time I reach a new row, I'm going to a new shell of electrons, I can tell how many valence electrons I have by looking at what column I'm in. So things in group 1A, that's to say hydrogen's column, they're all going to have 1 valence electron because they're the first column after we've started a new electron shell. So everything in that column has 1 valence electron, 1 electron in its outermost shell. Everything in column 2A is going to have 2 valence electrons, that is to say 2 electrons in their outermost shell. Everything in column 3A, that's the column that starts with boron, is going to have 3 valence electrons, 3 electrons in its outermost shell, and so on. This leads to some interesting side effects. For example, everything in group 8A, those noble gases, they all have a full outermost electron shell. That full outermost electron shell really affects the properties that these elements have. Likewise, everything in column 1A has one valence electron. The fact that all of those elements only have one valence electron means that they tend to have really similar chemical properties. So lithium, sodium, and potassium, these three elements, they're going to actually have really similar chemical reactions that they can play a part in. So the columns in a periodic table, remember columns are vertical, tell us how many valence electrons each element has. This only works for the A groups. You can see them labeled on your periodic table, 1A, 2A, skip the middle, 3A, 4A, 5A, 6A, 7A, 8A. These valence electrons are the electrons in the outermost energy shell, and they're the ones that determine how an element will react. So if two elements have similar numbers of valence electrons, they're going to react similarly. So all of these are the elements in that first column. Hydrogen, lithium, sodium, potassium, those are all in column 1A. All of these elements have one electron, one valence electron. So hydrogen is in the first row, that means it has one electron shell, and it's in the first column, so it has one valence electron. Lithium is in the second row, so it has two shells, 1, 2, and it's in the first column, so it has one valence electron. Sodium is in the third row, so it has 1, 2, 3 electron shells, still in that first column, so one valence electron. And then potassium is in the fourth row, so 4 electron shells, and again, first column, so one valence electron. So even though these elements get progressively bigger, they all actually have really similar chemical properties, because those properties tend to run in columns because the number of valence electrons runs in columns, and those valence electrons are the electrons that tend to get involved in chemical reactions. So I want you to take a moment and add some information to your periodic table. What I'd like you to do is go through, and on each row of the periodic table, I want you to write the number of that row. So you can see how both on the left-hand side and the right-hand side of this periodic table, I've written 1, 2, 3, 4, 5, 6, 7. Down at the bottom, it's important to note the lanthanide series is actually in row 6. The actinide series is actually in row 7. And I've done the same thing on the opposite side of the periodic table. So take a moment, pause this video, and go ahead and add that information to your own periodic table, please. So to review what we've done so far, we've talked about how the number of protons determines the order that elements appear in going left to right on the periodic table. We've talked about how every time you fill an electron shell, we're moving to a new row of the periodic table, and that as a consequence of that, properties tend to run in columns with the number of valence electrons. So things in column 1A have one valence electron, things in column 2A have two valence electrons, and so on and so forth.